Oh, just a little bit. All right, so today we've got kind of some random things that are all going to fit together at the end. So I'm going to pass this around. So what's going to happen when you look at this is that when you hold this up, and especially if you change like your perspective on it, you're going to see that fork. Part of it's going to look much bigger, part of it's going to look thin. And if you hold it up and you look kind of like down at an angle, it's almost like the fork is floating, like it's been cut in half. So depending upon your angle and how you look at that fork, you're going to see completely different things. So even if you just look at it, just the short image, like it's just like this, and then compare that to what it is up above, you'll notice that the image down below almost looks a little bit bigger. So it's almost like it's acting as a magnifying lens. So I'm going to do this so that what I'm going to talk about next kind of makes more sense. So I'll go out to the fish tank and we'll look at it there too. So we're going to look at two different scenarios. So scenario number one, we're going to go out to the fish tank and we're going to look at something inside the fish tank, okay? And that's what's happening now. You all are on the outside looking in at this. Now, what you kind of have to think through is the path of the light that allows you to see that fork inside of it. So that path of those photons are going to take is they're going to come in, they're going to bounce off the fork, and then they're going to bounce off, and then that's what you're going to see. So what's important is that when this is your eyeball out here. Okay, so this is you looking in. So the path that this is going to take is that as that light bounces off, or if you have a light bulb or whatever it is, like a point source, it doesn't make any difference. But here's what's going to be important. As that light comes out and it hits this glass, what's going to happen is that when it hits that higher index of refraction, okay, what's going to happen is that that's going to get bent like this, because this index of refraction is like 1.33. So it's going to hit that glass, and then it's going to get bent, and it's going to go like this. So if it's coming out at any kind of an angle, this is almost going to act like a lens. So it's going to hit this, it's going to diverge that light. This is going to hit, it's going to diverge that light. So when your eyeball is out here, what your eye does is that it tracks it back to where it looks like it began. So when you're looking at this, that light, if you trace that back, it almost acts like a lens. And this is going to come back here. So when you're on the outside looking in, the objects that it's going to appear is going to appear closer than what it actually is, because it's going to hit that higher index of refraction and it's going to get bent away from it, so it's going to get spread out. So it almost, like I said, almost acts like a lens. So this formula, and I will give this formula to you, you just have to know how to use it. So what it is that you're trying to figure out the image distance. So this image distance calculation is going to be the ratio of your two indexes of refraction times your object distance. So in this situation, the object is in reality 10 centimeters away. So in other words, if you look down from on top and you measure the distance from the glass to the fork, that would actually be 10 centimeters. Okay, that's your actual distance. You look down, boom, that's what you've got. So what this is getting you is what does it appear to look at? Jackson.
What's the word above and to?
Finish. Where you start and then where you finish.
What do you mean where you start and where you finish?
So in this situation, the light is going to start in this higher index of refraction. It's going to go through there. It's going to end up in air. So it's like, if you want to think of it as like in not over in.
So the start is the glass?
Yes, because that's where it's got to go through, and it's going to end up out here in the air.
What if it goes through different
It's
still just the
whatever
start
that
and
last
finish?
medium is,
Okay.
because that's what's going to determine where it's going to go.
And is that a multiply sign?
Yes.
With a dot? Okay.
Yeah. You're going to
Just
multiply it
making
together.
sure. I don't know. It looks kind of like a speckle. You know what I mean?
No, it's a dot.
I know. I was just making sure.
It's legitimate.
Yeah, the times
That was an
SO.
equal sign.
See, exactly. Good thing I asked.
Okay, but here's what I want you to see, is that when you're going from that high index of refraction out to a smaller index of refraction, it's going to appear closer. So the only way that happens is if you take the smaller index of refraction, where you end up, in this case with air, divided by that higher index of refraction, you get 7.5. So what's going to happen is that even though this looks 7.5 centimeters away, that's what it's going to appear to be. In reality, it's 10 centimeters away. So if you ever try and do like spear fishing, where you're looking at fish like down through the water into the shallows, the fish is going to appear closer than what it actually is because how that light's going to interact. Now, if you reverse it, if you're the fish looking out, okay, if you're the fish looking out, the opposite's going to happen. So you're looking at an object that's outside of that. So what's going to happen is that it's just the opposite. That light's going to hit that higher index of refraction, and it's going to slow down, and it's going to get bent closer to the normal. So as that gets bent closer to the normal, then it's going to shallow, these lines are going to shallow out. So now when you reverse it, your eye is going to trace this path back to a point further away. So if you're Frank the fish, and that's what's going to happen on today's assignment, if you're Frank the fish looking out, it's going to look like it's further away than what it actually is because of how that light gets bent.
So
Wait,
when we're at like an aquarium, we look small to the fish.
Well, because you're a little further away, a little bit smaller, yeah.
I'm confused on the light, like where it's coming from. Like,
Okay.
Can you can you
So-
explain your diagram?
So let's say, for example, this is a can of fish food,
Yeah.
okay? So here's the story. If you're the fish in here, to see this can of fish food, light has to hit the fish food, bounce off, and then it's going to go through that glass into the fish tank.
Okay, that's all we're worried about?
Yes,
Okay.
that's it.
Okay.
So the only thing that happens now is we reverse these numbers. So now you're going to get 13.3. So now what that means is if you're Frank the fish, you're looking at the fish can is actually going to be here. But it's going to appear further away.
Oh, so your like dotted line is what it seems like to be?
Yes. So
Okay.
because your eye is going to trace this line back to that point. Louis.
So if it's like the glass and then the water, do you have to go from the air to the glass and then the glass to the water?
You know, you just always look at it in terms of what that, it's just, when I'm going to make it simple, and we're only going to go through like that exterior glass.
Oh, okay.
Okay, I'm not going to make it complicated, we're
But
going to make like two different, because typically that glass, that index, water typically have about the same index of refraction. I'm not going to give you anything weird where it's like glass into like a diamond or something weird like that. You're just going to assume that these two have the same index of refraction.
Okay.
I'm not going to make it difficult. Okay, Jackson?
Is this just based off of perspective?
Yes, that's all it is. It's just based off perspective. So speaking of perspective, let's go to the back of the room.
It's like
So what you want to do is
Oh wait, I don't want to
stand
go
here
first.
and then walk and
that's like he's
see
following.
how that perspective changes.
Oh, that's weird. It looks way better on camera.
Really good.
So just, and you don't have to be that far away.
Oh man, this isn't looking too good. Sorry guys.
What happens?
It followed. Oh, it looks good. Whoa.
He's turning his head.
Yeah.
His head, right?
Yeah.
So it looks like he's following you as you walk past. Because what's happening is that you're changing the perspective of that shadow. Because
Oh,
this
sorry,
is
guys.
This is just like the negative, so you have a light source on the back. So as you walk past, you change that perspective, and it looks like he's following you.
I don't know if they can tell. Can you tell?
Can you tell? Are you asking the camera?
Oh, no.
Can you guys tell?
So here's mess with your mind number 2. So if you look at this, okay, right? So just everybody just kind of give that a look, right? So it just looks like your normal basic flat mirror. Okay? And you lean forward and remember, here's what's happening. For you to be able to see that image, if you go through the mechanism, light is bouncing off your face, right? Hitting the mirror, bouncing off, and going into your eye. So what you see is it looks like oh man, I'm back there, okay? I'm not because of that light bouncing off. Now, if I turn it on, whoa,
Whoa!
I love these.
and then look at it,
Wait, what?
you gotta look at it, you gotta
Louis,
look at
come
it
here.
front on.
Louis, come here.
Okay, I will. Don't worry, Jackson. I'm coming.
Look. Sam, you're in the way.
Why do you have to be that person?
Oh, it is.
Wait, why'd you do that?
That's insane.
So, what does it look like?
It's a tunnel.
It looks like a tunnel,
Wait,
right?
can I see?
Brake lights look like that.
Oh, that is weird.
Have you seen those? That looks so cool.
Okay?
It's crazy.
So what's happening is that obviously there's not a tunnel back here because we turn it off, boom, it disappears.
Wait, how'd you do that?
He turned it on.
I know, but like,
So what's happening
What
is
is
that
in
there's a
there?
series of LED lights around in a circle. And so what's happening is called like an infinity mirror. So what's happening is that it's continuously bouncing back and forth, back and forth. And so it looks like it's going to infinity, but it's only because of the fact that light internally is bouncing back and forth. So it looks like you have this incredibly deep tunnel, but you really don't. And again, it's just because those lights are on the inside and it's bouncing back and forth. And so what you're seeing is it looks like that tunnel, and even if you kind of change it, it looks like it almost curves a little bit. So, got that one. We're good. Okay. Now, over here.
Oh my gosh. It's all
Down number 3.
oh, he took my chair. Sorry, Jackson, I took your chair.
So
Wait,
all
actually-
this is water,
Should I
and
go
I'm
right
just
here?
putting in a little bit of calcium carbonate to
Wow.
just get some
Sodium
stuff
will be all right.
floating inside of it.
Are we calculating the KSP?
No, we're not calculating the KSP. This is just to get some stuff.
Oh my
in.
gosh, that was so funny.
So what I'm going to do is I'm going to shine this light for all the world to see. Okay. Now, so the cool part of what that sodium carbonate does is that it allows it to bounce off of that material. So you'll notice as that light comes in and it hits the water, what does it do? Which direction does it get bent?
Goes down.
Towards the normal, right? Because it comes in, hits the water, and it gets slowed down, so it bends downward, right? Now, if you do that right, you'll notice that it's going to come down, hit the bottom, bounce off of it, and then even reflect off that bottom. So this is going from, so what has the higher index of refraction, air or water?
Water.
Now, we're going to reverse it. So, yeah, okay, you're good. So now if I do this, okay, now if I go from,
Wow.
now if I hit this just right, here's what I want you to see. That as that light, there it is, over there, okay?
This is magic.
It's magic. So what's going to happen is if I hit that angle, notice that what happens is that if you look here, so it's hitting the surface of the water, that interface with the air, and then it's reflecting back down. So this is what's known as total internal refraction. So so if I'm going this way from air into water, that's never going to happen. Okay, I'm never going to have total internal refraction. And we'll go through the math later on and you'll see why this works. But if I go from a more optical, from a less optical dense, or excuse me, a more optical dense into a less, like if I'm trying to go out into air, then what can happen is that I can make that, all of that reflect back inside. So there's a critical angle, which we'll get into in just a second. So you'll notice if you look at this little dot right there, okay, so all that light is getting reflected back. Now, if I go shallow, then
I can't see anything.
it'll go up there. But if I go, so right now, kind of right there, it's hitting that and it's going parallel with it. But if I go steeper than that, what's happening is that it's hitting this, and this only works, and we'll go through the math in just a second. This only works if you're going from, like for water into air. It doesn't work if you're going from air into water. Because, and like I said, the math will make sense in just a second. So as this goes through, when you hit that total internal refraction, that light's hitting, it's trying to escape, it won't, and all of it gets reflected back. I can do it from more to less, but I can't go it if I can't get that to happen if I go from air into water. But what you can see nicely is that when it hits that point, it's going straight, boom, hits that, and it slows down, and it gets bent away from that vertical axis. Got it? Good? Okay, back we go.
In the atmosphere as well.
Huh? So, what this shows, this is polarizing film. And what it is a very, very, very fine mesh that's embedded in this plastic. So if I put this one up there, right, it kind of blocks out a little bit of the light, but not much. So basically what's happening is that that bulb is emitting all different directions of light, all in different directions. So if I take another piece of polarizing film and I put it over the top like that, you really can't tell a difference. But if I turn it 90 degrees, then you block
the
out the
heck?
light. If you turn it another 90 degrees, now if you're going in between, notice that you have varying degrees of light that's being let through. So what this is doing is this is supporting the idea that light in this situation is acting like a wave. So if you imagine like my fingers are like a fence. So what the first one is doing is that it's only letting light go through where the waves are parallel with the fence. So if I put this other one over the top of it, and I have another fence that's in line with it, that light is still going through it because the waves that are let through are parallel with the picket fence. Now, if I go to completely 90 degrees, now I've got two fences that are opposites of each other. Now, none of that light is allowed through because the light's going through one, it hits the other one that's a 90 degree to it, and you block out the light. So as you go like in between, then that's why it gets a little bit lighter, a little bit darker. As you're changing that and you're at more and more of a right angle to it, you're letting less and less and less of that light energy go through. Now, you take your basic protractor, okay? Not a big deal. I lay it up there. Light goes through, you can see the numbers, not a big deal. But, if I do this, so what happens with protractors is that protractors twist the light. So as that light is going through that bottom screen, you're only letting a certain direction of light go through. Then it's getting twisted as it goes through the protractor. Then what the second film is doing is that it's twisting that light so that you get different types of light that's being passed through and that's why you kind of get that psychedelic look to it. Now, protractors are cool. But you can also, there's also certain liquids that are we call optically active. So this is corn syrup. Okay?
Whoa.
Right?
Disgusting.
And those are just like air bubbles in there, right? Don't flip out and go, oh my God, it's alien. But if I do the same thing, and I twist that, okay, it's like a Picasso, right? So if I twist that, now what's happening is that that light is getting twisted again. So that corn syrup is doing the exact same thing that that protractor was doing. It's going to twist that light. Now, you try this with water, nothing's going to happen. So, Jen, hand me that beaker of water. So, if we try that with water, okay, nothing happens. Because water isn't optically active. Corn syrup is. Corn syrup twists that light as it goes through. The water just lets it go through with no interference whatsoever, and that's why you don't get the different colors that you do.
Can you like slosh the water in that?
Is glass optically active?
No,
So neither of them.
no.
Then
Is
how
that
come a
good? How much
protractor?
sloshing do you
How
want?
come a protractor
I want
is
max
optically
slosh.
active?
No, no, no.
Maximum
It's clear.
slosh. Max slosh.
No, that's max slosh right there. Okay.
Want all the slosh.
That was
available.
pretty cool.
Okay. So the other, if you've ever heard of like fiber optic cables, this is basically how a fiber optic cable works. So if I shine this light through it here,
Whoa.
okay,
Wow.
That's sick.
okay, so you can't see it as it travels through the acrylic, but you can see it come out the other end. So what fiber optic cables do is that it traps that light. So the whole idea of this is much like what's going to happen with the water back there. If you want to send light signals, and the advantage of light is that it travels at the speed of light, okay, pretty cool, hence the term fiber optic cables. And so then when I send that through, instead of sending like an electrical signal, which still travels pretty fast, but the fiber optic, because of the fact that it's going to travel purely at the speed of light, and what you don't want it to do, obviously I don't want to shine this thing, and then it hits this, and then it keeps going straight. Because if that's what happened, there'd be no point in fiber optic cables. Well, you could use them, but only if they went completely straight. Like, well, that's kind of boring. So, oddly enough, you kind of have to bend them and things like that. So, basically what we're doing is we're taking that advantage of that whole concept of total internal refraction. So when I do this, it shows up here because all that light is staying trapped within this and is traveling in a circle, and it comes out that end. Okay,
How do we like
math.
How do we, I guess, know what that information is once we receive it? I guess.
It's well, you basically decode it and send it into a series of bits of information that you can, like almost like a binary code, for like almost like a Morse code. It's like da 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 da, and then on the other end you basically transcribe that information back, and you can see an image of a squirrel, yeah, or a dog or whatever you're after. All right.
A cute dog.
Yeah, a cute dog at that.
Yeah, like my dog.
All right, so I need somebody to do some calculations.
Dude, don't call my dog a barefoot.
You have a Chihuahua?
No, it's a Japanese Shin. Shin.
It's really ugly.
You cannot call my dog ugly.
It has like a flat face.
Ugly. It's just so cute. It's just odd.
It's not ugly, it just doesn't look right.
It doesn't look right.
No, I think you're
Okay.
Okay.
So, by the way, the test is going to be on Wednesday, right? That's gonna work out well, because then you're all are off for Thursday for parent-teacher conference, so you guys have like a 4-day weekend. So the good news is, you don't have anything going on, no homework or anything over
Wait,
4-day
Tim,
weekend.
do we have the Monday off too for the President's Day?
Do we? Oh
No.
man.
That's
No.
They don't care about
4-day weekend honestly is not.
So here's what you should be able to do without any thought at all. Beam of light comes in from air, it hits water. Which direction is that beam of light going to get bent? Away from the normal or closer to the normal?
Towards the normal.
Towards the normal. Why?
Because it's a big.
You just gotta trust the process.
Trust the process.
Yeah.
Because of because of the index.
Trust
The index of refraction is bigger,
Yeah,
smaller.
so when it comes in, what's it going to do? Speed up or slow down?
What else would it be?
It's going to slow down. So this side's going to get hit. This side's going to slow down first, right?
Yeah.
Boink. Going to come down like this. That is something you have to have without fail. Okay?
Okay.
So how are you going to figure that angle?
That's the sign.
So
oh, is that
sine.
line in the middle the normal?
Huh?
Yeah.
That's a very curved line.
Okay.
N1 sine theta.
You thought it was like a lens.
I
or
know.
something?
I was like, I drew an X.
Better?
Yeah.
Okay.
Oh.
N1 sine
So-
theta 1.
So N1 sine theta 1 equals N2
Sine theta 2.
sine theta 2.
Theta, not theta.
So we've got 1.00 times the sine of 40 degrees. So we'll divide by N2, 1.33. We'll take the inverse sine of all of that. So what do you get as that second angle?
28.9.
What'd you get?
28.9.
28.9 degrees, which matches with what we said should happen, right? It's going to slow down, it's going to hit, it's going to get bent closer to the normal. Cool with that. Now, we're going to reverse it. Now, imagine here's the water, okay? So imagine I'm going to shine the light. I have the laser underneath the water. And I'm going to shine that laser out at 40 degrees. Index here is 1.33. And I want to figure out what this angle is going to be when it hits the water. So, when it hits from water going out into air, when it hits the air, which direction is it going to get bent? Further away from the normal or closer to the normal?
Away
Farther away.
Further away. Why?
Because it's the
Because
smaller. Yeah.
so it bends up.
It's going to speed up, right? It's going to accelerate. There you go. There's your acceleration term. So it's going to hit this, it's going to speed up. So is that angle going to be bigger or smaller than 40? It's bigger. So we can do this. We can go 1.33 times the sine of 40 degrees is going to equal 1.00 times the sine of theta. So we can divide by 1, take the inverse sine of all of that. What do you get for theta? 58.8 degrees. Okay? That was cool. Matches with what we said, right?
Normal.
Nice.
Yes.
Now, I'm going to make this angle even bigger.
Oh no.
Okay?
Want to.
So now I'm going to try 50 degrees. So now I'm going to bend that further out to 50. So then that's going to be 1.33 times the sine of 50 degrees divided by 1.
73.4.
Take the inverse sine of that. What do you get?
Oh no.
Undefined.
Undefined.
Becomes undefined.
Also known as 7 people.
Okay? Becomes undefined. So what that means is that if you're
Going straight up and down.
at 40 degrees, you can get an angle. If you're at 50 degrees, what's going to happen?
It's gonna bounce back.
It's gonna bounce back. So at some point, what would happen is that that light would get bent and it would go parallel with that surface. So anything above that is going to completely refract into it. So this is why this only works when you're going from a more optically dense into a less optically dense. So to get that critical angle, it's called theta C, which is your critical angle, which is going to tell you where you can go. So that's going to be the inverse sine of n over n naught, which in this case would be 1.00. And then we got 1.33. Yes, that's a 1 rower. And then that's an inverse sine. So somebody take the inverse sine of 1 divided by 1.33.
48.8.
48.8? So here's the deal. Here's how you can check this. So come back up here and let's try
48.8.
1.33 times the sine of, let's say, 48.7 degrees divided by 1. And then take the inverse sine of that.
87.7.
What'd you get?
87.7.
87.7 degrees. Getting really, really close to 90, right? So it's going to hit and it's going to bend way over, okay? Almost parallel with it. Now, if you try 48.8, try exactly 48.8. Take 1.33 times the sine of 48.8,
90 degrees.
90 degrees. So at that point, oh, it's going to be
Wait, so is that 90
Oh, man.
relative to the original angle?
relative to the normal. It's always relative to
Wait,
that
did I
normal.
do something wrong?
So that's going to be a 90-degree angle. So it's going to go parallel with
You can't do it over
that
there
surface.
more than one.
So why
The inverse sine of not one.
why is that bad?
what do you mean? It's not
Why did I
bad.
have to-
Like why is it like why can't you go more than that?
Because if you try anything bigger than that, this function becomes undefined. So if you go to 48.9,
Because he's exactly.
if you're above that, then what's going to happen? It's going to hit that interface, and then it's all going to bounce back in, and you'll have that total internal refraction.
something sign.
So if you're at exactly that angle, it's going to go parallel with it at 90 degrees.
So
Okay.
it's all gonna leave the
Is it because I'm in degree mode?
No, it's not going to leave. It's going to hit, and then it's going to go exactly along the surface of that water. If
I
you're
thought the normal was it's the
no.
normal.
Your angle is relative to the normal, which is a vertical. So here's the surface of the water.
Yeah.
Your normal is like this. Okay.
Oh, I get it now. Okay, I have it flipped. 'Cause
So if you're at 90 degrees to the normal, it's going to come around like this, and that water would go parallel with the surface of that water.
Gotcha.
Okay.
That makes sense.
Got it? Okay. Now,
But how do you find what the angle is if it's in the water?
that's what that equation tells you.
No, like if when it stays in the water, how do you know? Is it just?
Oh, no, it just bounces. There's no formula to determine that. It's just, all that tells you is the fact that it's all going to stay within that. And then you can treat it as a mirror, and then because it's all going to bounce in, then the surface is acting like a mirror, and these two angles are just going to be the same.
Gotcha.
Because it's just going to hit and it's going to bounce off of it. Okay? Yeah, then it's just literally it's a mirror equation at that point. Okay. So let's say you have a situation like this. So this is your surface of the water. You're 1 meter below the depth. You're going to shine a light this way.
Wait, this is water.
And Okay, so this is more of a, it's an interesting mathematical concept. So imagine that, and this could go either way. Either if you could, imagine that you're down here, and you could shine a beam of light where it would hit this surface, and then it would run parallel with it. So if you want to find this distance back here, where that's going to happen, where, in other words, how far back you have to be if this water is 1 meter deep, how far back would you have to be to shine that light where it would hit that, and then it would take off and it would go parallel with it, otherwise known as that critical angle. So if you look at this in terms of that critical angle, which is going to be the inverse sine of n over n naught. So let's start with that idea. So what that's going to allow us to do is that by itself would allow you to find that critical angle if you knew those values. Okay, you could get that if you wanted to. Simple deal. But now we're going to look at another one. If you look at this in terms of this angle, in terms of tangent. So tangent is what? How do you find tangent?
Opposite over adjacent.
Tangent is opposite over
Adjacent.
adjacent, right? So the tangent of that angle is going to equal the opposite over adjacent. Everybody cool with that? So my opposite is going to be that distance over 1 meter. Now, this is going to do a little bit of a substitution, right? So we need to find this angle, right? Well, that angle is going to be determined by that critical angle equation. So if we take this and substitute that in, then we go, okay, this is going to be the tangent of the inverse sine of 1 over 1.33. And if you do this math, to save you some hassle, okay, this is what I did with Eli's calculator while my AP chemistry kids were working on the lab, you get 1.14 meters, okay? So what this is, if you do all this math, and because of the fact that you also have to multiply that by 1 meter, okay? Because if you're going to solve for that distance, so it's going to be 1 meter times all of that. So that's where the meter comes from. So if you do this, you get 1.14. So what that means is if you were 1.14 meters away and you were to shine that light, it would hit that surface and it would run exactly parallel with that. Okay? So it's kind of a combination of geometry and optics. Now, here's the last one. And this is where lenses tie back into all of this.
Wait, so are we gonna have to do that on a test?
Oh, very real, yes.
The substitution?
Mm-hmm.
Then how come we just skipped over it so quick?
Well, there's a problem like it on your assignment. We'll spend more time on it.
We will?
Yeah.
Okay. I was gonna say, you were like, okay, let's just over. So yeah, I was gonna know what you did.
Another preschool days to learn about this.
Yeah. Remember last? We have two.
Two. I meant two.
It's a couple.
So not enough.
Yes, we did it. And that's all that matters.
What? Yeah.
Why do you object this
What?
Let's say without.
With,
It'd be W/O.
You should ask the TA to do the problem. she knows this, so honestly, nobody
Yeah.
agrees.
It's not if I know, it's
On the
you
board
guys
right
can
there.
do it. Duh. I mean, I can't read it, so I can't solve it. I'm sorry.
I'm a physics TA, not an English one.
Twice.
English is my third language.
Yeah.
Okay. So find the object distance for a lens, and no, I'm not going to tell you what kind of lens it is. With a focal length of 30 centimeters that will produce an inverted image twice the size of the object.
Are you kidding me?
I feel like we should start with the magnification thing.
I feel like we should.
Well, actually, maybe not. Or I feel like maybe we'll have to do some substituting. No?
A magnification is going to equal -2.
Yeah, no, that's what I'm saying. We know our
But then we don't
magnification.
know SI or SO. so
SSI
then we
over
don't
SO.
Or any heights, because you can also use height.
It's a lens, right? Okay, it's a lens. We know.
It's a lens. So let's start with what kind of
50-50
lens it's going to be.
Well, we don't know.
We do.
Well, if it, yeah, based off the image it produced.
Oh, wait, yeah, we do.
So could it be a concave lens?
No.
Why?
Because
It produces an upright image.
Because it produces concave lenses only produce,
diverging, virtual.
yes, virtual images that are upright and small. Can't be a concave lens. Only option is going to be a convex lens. So,
Oh, yeah. You can tell us it's a lens.
so this is where you have to be able to think this through. So this is going to be a convex lens, right? So let's say that, here's your arrow. This is the arrow, this is my object, okay? Notice how I labeled that object, okay? It's a convex lens. Where's the image going to be? Same side, opposite side.
Opposite side down.
So it's going to come through here, right? And then it's going to go through that focal length, like this, right?
Yep.
And then this one's going to come through here like this, okay? And so we know that's going to produce that inverted image. Now, because it's a convex lens, what's the sign of my focal length?
It's got to be positive
Positive, why?
because it's converging.
Because it brings the light together. Now, will you grant me that 1 over psi plus 1 over so equals 1 over my focal length? Standard thin lens equation, right?
Yep.
No worries. We know this is going to be 1 over 30. Is that 30 going to be positive or negative?
Positive.
It's a positive value. Now, let's do what Morella said at the beginning.
Oh,
Let's look at the magnification. Magnification is going to be what?
those.
2. So, what are the 2 ways you can calculate magnification? Now, just leave out the negative signs.
SI over so.
Psi over,
So.
Or high over ho.
but let's do it with psi over so.
You can make them equal to each other.
Oh,
Or something like
not so
that.
much equal.
Well, it'd be
Well,
like
what's the
psi over
only
so
way-
equals 2.
That I can get a magnification of 2
Something's double it.
is if my psi,
Twice as big as my so.
oh,
You're a genius.
So-
Honestly, I don't even know how to balance this time.
huh?
It's absurd. I'm just too smart.
It's a horrible burden.
I think he's ready for the test now.
Right, let's just bring it.
Honestly.
Test, boom. Monday, screw
Just
it.
leave all your
Okay.
things right there. We'll be alright.
Now, so here's my question. Could I come over here and put this as 1 over 2 so plus 1 over so equaling,
Yo, yeah, you could.
can I do that? Does that speak to you, Sam?
That's insane.
That's insane.
And then you know what you can do? You can combine
What can I do next, Sam?
Combine them together.
Okay, so how can I add,
3.
17.8.
so I can put this as 1 over 2 so, right?
Yeah.
Plus 2 over 2 so
Yeah,
equals,
common denominator.
They all equal 10, right? Wait, no.
no,
LOL. Just don't listen.
okay.
Which means that it's 3 over 2 so.
Oh, so it's 3 over
2 so.
equals 1 over?
30.
So now we can maybe do a little cross multiplication?
Yeah.
So if we get this, right?
90 equals
40.
So 3 times 30
That's insane.
is gonna equal
Nine.
to so. To so or not to so? So is gonna equal,
45.
oh,
This is cool. That's what I had.
or 10, if you round it up,
Yeah, I
okay?
rounded up by like 20.
So if so equals 45, so if my so is 45,
We
then
just need to find the object.
what's my image distance going to be?
We just need to find
90. So that's going to end up, so if this is 45, that has to be, now, does that make sense that that's outside that focal length?
it. Does.
It does, because that's the only way you can get an inverted image.
That's insane.
I know, it's crazy.
That just blew my mind. That's like magic right there.
Oh, I,
You know what else? You know what else?
so this is what's known as the fish assignment. Okay? The fish assignment. So this is your one chance
Oh, pressure.
to get extra credit.
Oh, really?
Now this is purely up to you. Okay? So what you're gonna have here is Frank the fish. Okay?
That's my dog right
So this is up to, and this is up to my discretion, up to my discretion of up to 10 points of extra credit. Okay? That will be added to homework, labs, wherever you need to fill in some points. Okay?
Test?
Not tests,
Aw.
homework or labs, but that's still 40% of your grade between the two of them. So here's just like the aquarium, and you got your water, and you got Frank, and you got a little starfish, and you got a plant. Okay. So this is purely up to you. Okay. If you want to color it, great. If you want to go, it's really not worth the time. That's up to you. Okay. So you've got 2 problems up here, oddly enough involving Frank the fish. Okay. And then you have some questions from your book and
It's like, what?
problems. Okay, this isn't all of it. No, there's a whole bunch
Wait,
of
is
questions
coloring the fish
and
there
problems.
extra credit points?
Yes, this is out of chapter 18. Okay, this is the third
You got page numbers?
out of 18.
Is there anything extra that we need to know?
No, you're
So,
good.
so what's extra
Refractions,
credit?
pages?
Coloring the fish?
Coloring the fish is the extra credit.
10
You
points.
better
for coloring
color
the
it really good.
It's up to you.
Oh, is it based on how many extra credit points that you think how good it is?
Yes.
Wait,
Is it
what?
like a
So if
competition
you
or
just
something?
like
You're
take a
judging
pencil
it?
and shade
Yeah,
in
that's
the
what everyone always
bubbles,
have.
at best you're going to get 1 point.
Oh, yeah.
Okay.
Wait, we get
Now, if you go hardcore, and I hate giving out extra credit
So
points.
if I put a bike on the fish, I'm pretty good at drawing
It's
bikes.
coloring, not drawing.
It's coloring.
It's his artistic
Like a glitter
expression.
Yeah, I'm very.
Glitter glue. Let's get some glitter glue.
How would you work a bike in this?
Nah, he'd probably get
Give
mad
him
if
legs.
he
The fish is
And
riding
then
a bike.
it writes itself from there, to be honest.
Or it's part of the
Why don't you just
environment.
color the fish?
Just trust.
Maybe we should make a
Because it's
fish
his
family.
artistic
Can I make a
expression.
spearman ahead of it?
Yeah.
Spearman?
If I make a bike,
What?
15 extra credit.
Like a person shooting it with a spear?
No, no, this is a family show, okay? No, I don't want somebody up above, like, no, don't go that, no, and it's not gonna get on fire either,
Mr.
okay?
Burkamp, do you go hunting?
No.
Yeah, you don't seem like the type. I was
Oh,
gonna
God,
say.
no.
Me
I've
neither.
tried it, and it
Just
just
can't get
didn't
behind
end
it.
well, because I'm a
You
horrible
tried
shot, burns
No,
come
I
and land on
haven't.
the
I
end
never
of
even
my
held
gun,
a
so
gun,
it's-
bruh.
Okay, so I'm done. Just do on Monday. Like I said, purely optional. So what we typically do is that to get in the mindset of the test, we'll cut them out and we'll glue them up around the room. Okay? And you can, and then maybe at parent teachers conference, you go, oh, go see the fish in the room. Okay?
Wait,
So
are we gonna
cool.
go see the fish out there? Were we supposed to do that today?
I don't know.
We already saw 'em.
Yeah, but where are we supposed to go visit them again?
We could if you wanted.
I don't.
Sam wants to.
We'll do that on
Well,
Monday.
we
How
want
about
to.
you? Okay, all right, so
You
stop
don't
that.
drop me in